All right, let's just jump right in, shall we? We're going to tackle one of the biggest questions, maybe the biggest question you could ever ask. This isn't about some small new discovery. We're talking about an idea that tries to explain, well, everything.
But, I mean, how do you even start with something like that, right? If someone walks up to you and says, hey, I have a new idea about where reality itself came from, what's your next step? How do you take that huge, almost philosophical thought and actually test it in a lab? That's really the core of what we're digging into today.
Okay, so here it is, the specific idea we're putting under the microscope. It's a big one, a speculative hypothesis. It basically says that everything, and I mean all matter, all forces, the whole shebang, pops into existence from a single source. That source is called the zero-point energy field. You can kind of think of it as this constant underlying hum of the universe. And the mechanism? A process called Constraint-Resonance Emergence Theory. We'll just call it CREET for short. This is our big mystery.
So let's officially bring our new suspect into the station. For, decades now, the case has been pretty much closed, right? The reigning champs, the top dogs explaining our universe have been quantum field theory and general relativity. But now this ZPE plus CRET idea, it's a brand new contender, a totally new suspect in the ultimate cold case. Where did all this stuff come from?
But see, in science, just having a suspect isn't nearly enough. You need a detailed profile. You have to turn that big, grand idea into something really concrete, with specific, identifiable features that our detectives, in this case experimental physicists, can actually go out and look for.
And this is how you build that profile. It's basically a three-step process. First up, you define its identity. What are its fundamental rules, its mathematical symmetries? What makes it tick? Second, you define its interactions. How does it talk to everything else we already know exists, like matter and energy? And third, you got to define its signature. What unique fingerprint, what scientists call a vacuum fluctuation spectrum, does it leave behind on reality for us to find? Without these, it's just a cool idea, not a theory you can actually test.
This brings us to a really, really important word: falsifiable. You got to remember this one, because it's the absolute bedrock of all science. A theory isn't really a theory unless it makes predictions that you could, in principle, prove wrong. Think about that. If there's no experiment you could ever do to show an idea is false, then it's not science. It's something else. It's a belief.
So now that we've got a profile for our suspect, it's time. Time to drag it into the interrogation room. We're going to run it through what you could call an experimental gauntlet, a series of intense kill or confirm tests that are designed to check its story against the hard facts of reality. First up in the interrogation is something called the Casimir effect. Now, this is a wild phenomenon. You take two uncharged plates, stick them in a perfect vacuum, and they get pushed together by, well, something. It's a direct probe of the vacuum itself, which makes it the perfect first test for an idea that's all about vacuum energy.
Let's look at the specifics here. The theory has to spit out a number, the exact pressure between the plates based on how far apart they are. So why is this a good test? Well, because it pokes and prods the vacuum directly. But the most important part is the falsifier, the kill shot. If the theory's prediction doesn't match the measured force perfectly, if it's off on how the force changes with distance or temperature, boom, the theory is wrong. Done.
All right, next test, we're bringing out the big guns now, atomic clocks. And I'm not talking about the clock on your wall. These things are so unbelievably precise, they can literally detect tiny warps in space-time. They are the ultimate tool for hunting down brand new physics.
So for this one, the theory has to predict if it causes any tiny shifts in the energy levels of an atom, which would actually change the tick of the clock. It's an amazing test because these clocks are accurate to 1 part in a quintillion. That is just insane precision. And the falsifier? It's beautifully simple. If the CREET theory predicts a shift but our best clocks don't see anything, the theory's out.
And for our third and final interrogation, we're looking at gravity. But we're not looking at planets and stars. No, we're zooming way in, looking for any weirdness in the force of gravity at incredibly small sub-millimeter scales. This is where new forces or strange effects might be hiding in the shadows.
Here, the prediction is all about any deviation from Newton's classic inverse square law, but below a millimeter. The tests use these super-sensitive torsion balance experiments, and the falsifier here shows you just how hard this is for a new theory. If it predicts any deviation that's bigger than the limits we've already measured, it's immediately dead on arrival. This shows you how much existing data can already box in a new idea.
So,
We've run our suspect through the gauntlet. Now what? Well, it's not about any single test winning or losing. Science is about weighing all the evidence together, looking at the whole picture before you even think about reaching a verdict.
And this really is the main event. In one corner, you've got the predictions from our new suspect, Crete. It has to bring something new to the table, something we can measure. And in the other corner, you have standard physics, quantum field theory, general relativity, the undefeated champions that have been tested to incredible accuracy for decades. The new guy doesn't just have to be right, it has to be more right.
It's a super rigorous four-step process. First, you get the model down on paper, mathematically, with a few new parameters. Second, you use that math to calculate what your theory predicts for all those tests we talked about. Third, and this is a big one, you do a global fit. You use some heavy-duty statistics to see how your theory stacks up against all the existing data at once. And then finally, if it's still standing, you make a forecast. You tell other scientists, hey, if you build a better experiment, here's the new thing you should find.
So, let's get to the bottom line. After all this, what have we really learned? What does it actually take for some wild new idea to graduate and become a serious scientific theory? Let's just boil it down. An idea is just an idea until you write down the math, period. And it absolutely has to predict at least one specific numerical thing that's different from what we already know. The bar is incredibly high. Our current experiments are so precise that huge parts of a new theory could already be disproven by data that's just sitting on a server somewhere. And this last point is so key. If your new theory just perfectly predicts everything the old one did with nothing extra, then it's not really a new theory, is it? It's just a different way of telling the same story.
And I think that's the perfect question to end on. This whole process, this gauntlet, it forces us to ask something really fundamental about discovery itself. If a new idea, no matter how beautiful or elegant it sounds, doesn't point us to something new, something we can actually go out and test in the real world, is it even a new scientific theory at all? It's a question that gets right to the very heart of how we as humans figure out how our universe works.